In addition to the phenomenon of reflection discussed for wave on a string in section 17.3, we also found that some of the energy of the incident wave transmits, into the new medium. For this case, a pulse, incident pulse, is moving from lighter string to the heavier string. So this is a boundary. For this case, in opposite, incident pulse is moving within the heavier string, meeting a boundary, then going to be transmitted into lighter string. Okay, what will happen? The incident pulse here, going to be reflected, but part of it, for this case, from lighter string to heavier string, the reflected back pulse will be inverted, and then another part of the pulse going to pass through the second medium. For this case, right, the reflected pulse, this one is not inverted, right, and transmitted pulse, this one, move on the lighter string, right. Similarly, when a ray of light traveling through a transparent medium, let's say from air here, encounters a boundary, where we have air glass boundary here, right, leading into another transparent medium, which is as this figure, part of the energy is reflected, this one, reflected ray, right, and parts of the energy going to passing through the medium. This ray, we call it refracted ray. The speed of the incident ray going to be higher in air compared to the glass. For that consequence, the refracted ray going to move nearer to the normal line. As in law of the reflections, incident angle must be equal to the reflected angle. Alright, theta 2 here is refracted angle. So, based on the analysis of the speed of the wave just now, right, sine theta 2, ratio to sine theta 1 is equivalent to ratio of V2 over V1, right. All rays and the normal lie in the same plane. This is the condition, and the refracted ray is towards the normal because the V2 is less than V1, slower, right, because this one, the refractive index is higher compared to air, right. Now, when the light beam move from air into the glass, for the first case just now, the light slow down upon entering the glass and its path is bent towards the normal, as I mentioned just now. But when the beam move from the glass into the air, the light speed up, upon entering the air in its path is bent away from the normal. Alright. And happen to be, if we do some sort of analysis, this is the incident ray, right? So actually, the emerged ray out of the glass going to be parallel to the initial or incident ray from the beginning, right? So this is a mechanical analog of refraction. If let's say we use a barrel, and the barrel is moving from concrete region, and then going to meet the barrier of a concrete grass boundary, so what will happen, the speed of the barrel going to slow down as it's going to enter second area here, the grass, Okay, so when this slow down, it shows that it's going to be bent because it slow down, right? This end slow first, that's why it's bent. As a result, the barrel turns. Okay, this is the mechanical analog of the refraction. Why is it the refracted ray is approaching the normal line or near to the normal line, right? So from here we can define the index of refraction for the material. For example, just now from air to glass. So the index of refraction for the glass, for example, is a ratio of the speed of light in vacuum, which is in our syllabus we consider vacuum as similar to the air, over the speed of light in the medium itself, the V. Okay, and we know that the speed of light in vacuum is the highest of all, which is 3 times to the power of 8 meter per second. Alright, so always the n will be bigger than 1 because this is always bigger than the V. This is smaller all the time. So the n always bigger than 1, bigger than the unity. Right. So this is how we define the index of refraction for a material. So you may refer to this table to check the value of the index of refraction. So if you see here, always bigger than 1. So now let's move to Snell's law. So what happened actually? Okay, whenever the wave or light is moving from, let's say, medium 1 here, okay, entering the medium 2 here. So if, let's say, okay, the speed of the wave within medium 1 is V1, is bigger than the speed of the wave in medium 2, which is V2, right? So actually what happened here, as the wave moving from medium 1 to medium 2, okay, the frequency of the wave remain the same. The frequency remain the same. But we know that the speed is changed. Okay, V1 is higher compared to V2. The speed of the lights of the wave is different. So it means that lambda must be different if this one to be the same. Why is it the frequency must be the same? Because the frequency with which the wave passes an observer, let's say, at point B, right, in medium 2, must equal to the frequency at which they pass point A. Okay, if this is not true, okay, what will happen? Okay, the energy will piling up here, right, or disappearing at the boundary. Okay, and we know that this is not going to happen because energy must be conserved. Alright, that is why the frequency must remain the same. Due to the V is different, lambda also going to be different. Based on the concept of F1 is equivalent to F2 is equivalent to the F, okay, then we may use the ratio like this. Lambda 1 over lambda 2 is equivalent to V1 over V2 equivalent to C over N1, C over N2, where C can be cancelled out, so we are left with N2 over N1. So from here, okay, we may rearrange the equation. Lambda 1 N1 is equivalent to lambda 2 N2, right? N is equivalent to lambda in vacuum over lambda within the material, right? And always lambda in vacuum, okay, always bigger than lambda within the material. So why is that the other n here? N for vacuum is 1, right? So based on this, we may also rearrange the equation, have some sort of this. N1 sine theta 1, okay, is equivalent to N2 sine theta 2. This is what we call it Snell's law. Okay, actually it's coming from this derivation. Alright, example 34.3, an angle of refraction for glass. A light ray of wavelength 589 nanometers traveling through air is incident on a smooth flat slab of crown glass at an angle of 30 degrees to the normal. Find the angle of the refraction. So based on Snell's law, N2 sine theta 2 must equivalent to N1 sine theta 1. So our interest is to solve the theta 2 given to us the theta 1. Right, and we know that it's moving from air to the glass. The refractive index of the glass you must figure out from table within your textbook, which is equivalent to 1.52. Right, so from here you figure out that theta 2 is equivalent to 19.2 degree. B. Find the speed of this light once it's entered the glass. So as we know, V equivalent to ratio of is from N is equivalent to C over V. So to have V is C over N. Okay, so and speed of lights is 3 times 10 to the power of 8. You may also have this value, the C, from your calculator, right? What is the wavelength of this light in the glass? So based on lambda, N is equivalent to lambda in vacuum over N. Lambda in vacuum or air is 589 nanometer over the N of the glass. You have 388, which is smaller compared to the lambda within air or vacuum. Example 34.4, light passing through a slab. A light beam passes through medium 1 to medium 2, with the latter medium being a thick slab of material whose index of refraction is N2. This is a slab with N2. Show that the beam emerging into medium 1 from the other side parallel to the incident beam, or this is the one that Madam explained to you just now, it should be parallel. So we have to show that it is parallel. Then you have to play around with the angles. Okay, so based on Snell's law, from medium 1 to medium 2, okay, and then another analysis, right, which is from the glass or slab to the air again. So you have here N2 and theta 3 here for this situation, emerging situation. Okay, so you have N1 sine theta 3 is equivalent to N2 sine theta 2. Sine theta 2 is equivalent to this. So it is substitute here. This is equivalent to sine theta 2. Right. So if you see here, we can cancel out this. We can cancel out this. And then we have sine theta 3 equivalent to sine theta 1. It is proof that theta 1 and theta 3 is the same. Therefore, we are proving that ray, the emerging ray here and the incident ray here is parallel. Okay, what if the thickness T of the slab is double? Does the offset distance T also double? Okay, so what are we going to do is cos theta 2 equivalent to T over A. Alright, thickness over A. Okay, so from here, A equivalent to T over cos theta 2. And then we know that T over A is sine gamma. Alright, D over A sine gamma. And what is gamma? Gamma itself is theta 1 minus theta 2. Right? From here, you substitute the value of the A and also to this equation. Then you will get this kind of. For the given incident angle theta 1 here, right? Okay, the refracted angle is theta 2 is determined solely by the index of refractions. Okay, so the offset distance D is proportional to the T. Right? If the thickness is double, so that's the offset distance D. So D is, so from here we know that D is directly proportional to the T. So if the T is double, then the B also going to be double. So now Huygens principle. Huygens principle is a geometric construction, okay, for using knowledge of an earlier wavefront to determine the position of a new wavefront at some instant. Okay, what is the Huygens principle? It states that all points on a given wavefront are taken as point sources for the production of spherical secondary wavelets. So the keyword spherical secondary wavelets, right, called the wavelets that propagate outward through a medium with the speed characteristic of wave in that medium. After some time interval has passed, the new position of the wavefront is the surface tangent to the wavelets. Okay, the keyword wavelets, okay, surface tangent. Alright, so how does this happen? Like this. Okay, if let's say you have originally, okay, wavefront is spherical wavefront. Okay, so let's consider 3 points here as the sources of the wavelets. From this one, okay, is going to produce new spherical wavelets. Right, for this one, for this point source, it's going to produce another spherical wavelets. Okay, again for this, another spherical wavelet. Tangent, okay, to the wavelets, to the spherical wavelet just now, the tangent line, okay, that is represented by B to P prime here, is the new wavefront from the old wavefront here. It propagates in that manner based on Huygens principle. Okay, this is for a plane wave. For spherical wave, okay, again the idea is the same. The old wavefront, every single point on the old wavefront going to produce or is the source of the new wavefront here. How to do it? Consider a point, okay, this point source going to produce one spherical wavelets. Okay, for this point of source is going to produce another spherical of wavelets. The distance, okay, travel from this point source to this wavelet at any instant is equivalent to C delta T, based on C, speed, is equivalent to distance over time taken. So distance only is C delta T. Alright, then for this one, this is its spherical wavelets. For this one, this is its spherical wavelets. So tangent line, okay, for the wavelets is new wavefront, where the V of this wavefront is the same to the V of this wavefront. That is what Huygens principle talk about. For the law of reflections, okay, let's refer to this figure, right? The line AB here, okay, represent a plane wavefront, So one wavefront, okay, of the incident light just as ray 1 strikes the surface at point A. At this instant, the wave at A sends out a Huygens wavelet, okay, appearing at a later time as the light brown circular arc passing through point D. Right? So this is the wavelet coming from point A. The reflected light makes an angle of gamma prime with the surface. At the same time, the wave at B, okay, emits a Huygens wavelet, the light brown arc passing through point C here, with the incident light making an angle of gamma here from the surface. Okay. This figure shows these wavelets, alright, a time interval delta t, after which ray 2, another ray 2, strike the surface. Right. Because both ray 1 and ray 2 move with the same speed, okay, we must have AD is equivalent to BC is equivalent to C delta T. The base idea, AB equivalent to BC equivalent to C delta T. Right. The remainder of our analysis depend on geometry. Notice that the two triangles ABC and ADC are congruent because they have the same hypotenuse of AC. Right? And because AD is equivalent to BC. Okay. From that, we can show that cos gamma is equivalent to BC over AC and cos gamma prime is AD over AC. Okay. Where gamma is equivalent to 90 degree minus theta 1 and gamma prime is equivalent to 90 degree minus theta 1 prime. Because AC equivalent to BC, this is supposed to be because AD, okay, is equivalent to BC, okay, cos gamma is equivalent to cos gamma prime. It means that gamma and gamma prime is the same. So it means that 90 minus theta 1 is equivalent to 90 minus theta 1 prime. It proves that theta 1 is equivalent to theta 1 prime. This is the law of the reflections, okay, that we've already learned just now. So it is proved that Huygens principle is applicable for law of reflections. Okay. Now let's consider this diagram. We are going to use Huygens principles to derive the Snell's law. Right. We focus our attention on the instant ray 1 again, strike the surface and the subsequent time interval until the ray 2 going to strike the surface as in this figure. Right. During this time interval, the wave at A sends out a Huygens wavelet, the light brown arc passing through point D. Right. And the light refracts into the material, making an angle of theta 2 here, with the normal to the surface. In the same time interval, the wave at point B sends out Huygens principle to point C, okay, producing wavelets, arc wavelets at point C. Okay. And the light continues to propagate in the same direction. Because these two wavelets travel through different media, the radii of the wavelets are different now. Okay, the radius of the wavelet from A, which is AT, okay, equivalent to V2 times delta T. Okay, this one. Right. Where V2 is the wave speed in the second medium. Right. The radius of the wavelet from B, here, okay, which is here is the wavelet, okay, is equivalent to V1 times delta T, where V1 is the speed of the lights in the original medium. This one. From triangles of ABC, again, ABC and ADC, alright, we find that sine theta 1 equivalent to BC over AC equivalent to V1 delta T over AC, and sine theta 2, okay, this one, is equivalent to AD over AC equivalent to V2 delta T over AC. Okay, dividing this first equation by the second, okay, if we divide this by delta T, it will give us sine theta 1 over sine theta 2 equivalent to V2 over V1. And we know that V is equivalent to C over N1 for V2. And for V1, okay, it's C over N2, right? So from here, we can have a cancellation of C. Then we will left with N2 over N1. And from here, we may rearrange the equation. Then we're going to have N1 sine theta 1 is equivalent to N2 sine theta 2. This is Snell's law proved by using Huygens principles. Total internal reflections. Total internal reflection is actually an interesting effect, okay, that can occur when light directed from medium having a given index of refractions towards one having lower from high refractive index material to lower refractive index of medium one. So from higher index of refraction moving to the lower. This is for total internal reflection to happen. So as we see here, okay, ray from ray 1 here, it might move straight like this. If it is normal, then nothing happen. But if it has certain incident angle, okay, when it meets the boundary, okay, the ray going to be reflected in certain manner. Right. For the case of this, okay, for the case of this, the incident angle, okay, when is known as critical angle, because the refracted angle is skimming the boundary. Okay, if you see the statement here, as the angle of incident theta 1 increases, the angle of refraction theta 2 increases until theta 2 is 90 degree, ray 4. The dashed line indicates that no energy actually propagates in this direction. For even larger angles of incidence, total internal reflections going to happen or occurs as ray 5. The angle of the incident producing an angle of refraction equals to 90 degree is the critical angle. We call it theta C. For angle greater than theta C, all the energy of the incident light is reflected. Okay, so to have total internal reflections, at least the incident angle must equivalent to or bigger than the critical angle. And this is where we have n1 sine theta c equivalent to n2 sine 90, which is sine 90 give you 1. Therefore, this side you are left with n2 only. This is only going to happen whenever the lights or wave traveling from higher index of refraction to the medium with lower index of reflections. Okay, so many application of total internal reflection. For example, in diamonds, how we cut the diamond. The way we cut the diamond actually going to give total internal reflection effects. Okay, where the lights that entering the diamond is going to be captured in terms of, okay, within the diamond itself. So we see the diamond glowing, okay, so beautiful. All right, and then another application, we also can have total internal reflection effect within cubic zirconia. Total internal reflections happen, and that is how we see the material so nice, so beautiful, because the ray is captured within the material. Okay, example 34.6, a view from the fish eye. Okay, find the critical angle for an eye water boundary. Assume the index of refraction of water is 1.33. So, as we know, okay, originally, n1 sine theta c is equivalent to n2 sine 90. This is the condition for total internal reflection to happen, where the incident angle equivalent to the critical angle. So sine 90 give you value of 1. That is why we can simplify the equation into this. Then you have this, and from here you figure out your theta c is 48.8 degree. So means that this is the minimum angle between water and air boundary, so that the total internal reflection going to happen. What if a fish is in a still pond, looks upward towards the water surface at different angles relative to the surface as in the figure? What does it see? Because the path of the light ray is reversible, so just now for total internal reflection, from high refractive index material moving to the lower refractive index of material. So for this case, the light ray is reversed. A fish looking upward toward the water surface, as in this figure, okay, can see out of the water if it looks toward the surface at an angle less than the critical angle. So the theta here must be less than the theta c of the medium. Therefore, when the fish lines of vision, this one, right, the fish line of vision makes an angle of theta equivalent to 40, for example, with the normal to the surface, for example, light from above the water reach the fish eyes. Okay, at 48.8 degree, which is the theta c, the critical angle of the water, the light has to skim along the water surface, as we know just now, right, before being refracted to the eyes, to the fish eyes. At this angle, the fish can in principle see the entire shore of the pond. Okay, an angle greater than the critical angle, the light reaching the fish comes by means of total internal reflection at the surface of the light originating in the water. Therefore, at, let's say for example, 60 degree, okay, the fish see a reflection of the bottom of the pond. Okay. So the application of the total internal reflection is one of the most famous is optical fiber. That is how we can pipe up the information or wave within optical fiber, because the optical fiber made up by glass, so that the wave that transmitted into cannot passing through, because total internal reflection happen at every single point, right? So the information that transmitted, or wave that transmitted, or lights that transmitted into optical fiber will be passed for a long distance without any loss, right? So this how on principle to create optical fiber. We have a glass or plastic core, and then we have a cladding, and then we have a jacket. Okay, the purpose of it, just to make sure that all the wave that transmitted into the glass or plastic core here, okay, keep on experiencing total internal reflections. So application of it, so many, tremendous of it. We can name it. Okay, our daily life really depending on this actually. Okay, that's all for this topic. Thank you.